for the last talk of our session. We're going back to MARLO, and let's welcome Valliappa.
So I'll be talking about a few approaches to MARLO, essentially, and in general, just multi-agent reinforcement learning with multi-agent, multi-task reinforcement learning problems. And this is joint work with a few people who I worked with at Deep Learning Camp. So let's start with the reinforcement setting, which I'm sure familiar with. So essentially, you have agent in your environment, and you have a markup decision process that you usually assume, and the usual goal is to maximize the expected return. The important thing is you can have other goals, and that's something we'll talk about. So as far as the environment is concerned, so MARLO is this long, it's an abbreviation that's quite long, and MALMO itself. So Minecraft is quite a modern game, 32 years after 2600, so it's a lot more complex, and it breaks a few of the RL assumptions that we commonly assume. So firstly, you have this inherent complexity in the domain. So this is even in the single task, single agent setting, right? This is, for example, partial observability, where you have to move towards partially observable markup decision processes. The other thing is open-endedness. So MARLO is structured in a sense. So you have these, reward signals that are given to you and tasks that are given to you, but Minecraft by itself doesn't actually have any of that. So you can look at things like curiosity-driven exploration and things like that. And the other thing is like which is in some sense motivation for our approach is that the simulations are expensive, right? So with a single Minecraft client, you can get up to about 1,000 steps per second, and this is excluding any agent overhead. So with a random agent, you get about 1,000 steps a second. And then finally, the state space and action space are very large. And then MARLO itself adds, the problem of multiple tasks and multiple agents. And particularly with multiple agents, you again add more partial observability and stochasticity if the agents are not deterministic, the agents that you're picking. So the approach we consider is world models. And what world models does is it's basically a model-based reinforcement learning setting, right? And so it first starts by learning a representation. So what it does is it uses, so this is work by Schmiduber and David. And so what they do first initially is to learn a variation autoencoder, right? So given a state, you learn to reproduce a state, but you also have this prior over your hidden representation that's, multivariate Gaussian distribution, right? That you're trying to keep as well. So in the first part, you're just learning the representation for the states, right? There is no actions involved here. There's nothing else involved. Just learning how to represent states. So after testing this, you can see. So OF here refers to observed frame, and RF refers to reconstructed frame, right? So this is the input, and that's the output. And you can see some examples here where it's learned, to do an okay job of representing the input frame. One interesting thing you can do with the fact that you have this multivariate normal distribution is you can do interpolation over over your latent space. So for example, here I'm given two states, and I'm asking to interpolate between the two. And you can see that clearly there appears to be some feature in the latent space that talks about the presence of this blue block, right? And so this is something that's really useful in the sense when you're learning a model, you want this property to hold. You want things to be continuous in the sense that each feature should represent something in the world, right? That's something that you get. So on the other hand, when you look at model-free agents, so this is from during DQN, a paper published a few years ago, and here what they did was they also tried to look at what the network is learning, and here they found that so in this architecture they essentially have two heads, they have a value head and the advantage head. So the advantage computes how much better each action is compared to the best action. And here what you can do is you can, so this is model free again, so there's no model-based component here. You can see that for the value head, it focuses on certain parts of the state, and for the advantage head, it focuses on other parts, right? So in terms of being able to understand your network or what it's doing, you get very different things. So with model-based learning, you're able to represent states and the state representation. Whereas here it's very strictly kind of combined with the task you're actually learning, right? And then that's kind of the difference between the two. So one takeaway from this is that it's probably better to make sure that your state representation learning and your policy learning are separate in some sense. But when you combine them, this is a problem with when you have multiple tasks. So when you have multiple tasks, it becomes hard to learn the state representation, kind of in some sense for each task in a different manner, right? So with in model-based learning, what you're doing is you're learning the state representations in a different manner, right? So it essentially allows you to separate the policy learning and the state representation. So that's one nice thing about doing this, right? So then, as far as the second step is to actually learn your transition, right? Your transition matrix and your reward function. And there are many ways to do this as well. So the approach taken here is to essentially use LSTM as well as a Gaussian mixture model. So with the Gaussian mixture model, you're able to sample next states. So in this case, you're given a state and the action, and you're able to produce next states. That's essentially what you get, right? And this is useful because, so I guess one reason for the LSTM is that, again, Minecraft is partially observable, right? And since Minecraft is partially observable, you have to have some sort of memory in it, right? And that's kind of the reason for adding memory. So one approach is to just add external memory, and this is something that we saw that we worked on in this work on memory queue networks, where you have an attention over your states as you act, right? And so as you see in the video, essentially these tasks are partially observable. They're, first task, for example, here is to, based on this indicator, with yellow visit, I guess, blue or red, and then green visit with blue or red. So here you strictly require memory to be able to perform the task. And as you can see for this task, as it goes to the end goal, it takes strong attention on the important state. Right? That's one way of doing, incorporating memory. But there's actually a problem when we want to learn this transition matrix, right, and the reward function. So if you go back to past work, so this is, I think, one of the first work that actually worked on trying to learn action condition video prediction. So I'm given an action and a state, I try to predict the next state, right? That's the main problem. So in the original work, it was assumed that this function is deterministic, right? So given a state and an action, the next state is completely determined by the state and action alone. And this is not necessarily true in a multi-agent setting, right? Multi-agent setting, other agents do things that I have no idea what they will do, right? So so for this reason, we actually need something that is a generative model, right? So you can't use a discriminative model like this, which just predicts one next state given your current state and action, right? And so this is an important thing to make note of. So actually, if you think about it, you can also do some other interesting things with the fact that you have a generative model. So there's been some recent work on using distribution reinforcement learning, where you learn the value distribution as opposed to learning the expected value for a given action or for a given state, right? For a given state action or a given state. And it's actually possible to use this idea here, right? So what you can do is, this is in some sense a version of approximate dynamic programming, because what you can do is, I'm given a current state and an action, and I have I can basically sample over all next states, right? Since I have a Gaussian mixture model, I don't have just one next state that I'm predicting. I can sample multiple next states. And so what I can do with this is, I can actually learn based on this temperature parameter tau, which tells me the probability of that next state. I can actually learn value distribution for the current state, right? I can look at what all the next states are and how likely they're going to appear, and then actually do this approximate the dynamic programming update, where I'm given my next states and then I can learn a value function, and then I update my current value function for the state that I'm at. And so why would we want to learn a distribution, right? So this is a question that many people have been asking, and I think one reason is with distribution RL, you can get a sense of the agent's confidence, right? And this is important in a multi-agent setting because you don't know what other agents might be doing and things like that. And in different states, it might be important to understand how confident you are of something that's going to happen. So in this case, what we're actually doing is we have these extra parameters that can also, so this is related to implicit quantile networks. I don't know if you're familiar with that word. But what it does essentially is it uses a uniform distribution, and it learns the actual bounds for the uniform distribution over time. And you can see that it gets wider as it's more uncertain of the value. So as it falls to the end here, you'll see that it actually becomes wider. So in some sense, this is a notion of risk, right? So how uncertain an agent is about its current state. And you can use this in multiple ways. You can, for example, use it from a safety perspective, where by saying if I'm uncertain about a state action pair, I will not take that action. Or you can use it from the other perspective when you do transfer. So in this case where we're doing multiple tasks, what you really want to do is you want to be able to estimate your value, your values really well when you move from one task to the next one, right? So for transfer, what you want to do is you want to do max entropy sampling of actions, right? So the action that has the highest value distribution entropy, which has the most uncertainty, is the action you want to take to improve your estimate. And then finally, so in the first two parts, we just learned our state representation, and then we learned the actual transition matrix and the reward function, right? So finally, we actually have to learn a policy, so how to act. So what we can do there, so in the original work, what they did was they used covariance matrix adaptation, which is AIIDE. So it's basically a way of doing essentially hill climbing. So and it's possible to do this because they're basically very small number of parameters. So it's on the order of a few thousand parameters. And this is because we moved most of our parameters to the previous task, right? So now I think in the original paper there were about a few million parameters in the actual state representation part, so the part that learns how to represent frames, and then a few thousand in the a few thousand in the LSTM one, and then here the least number of parameters. But we don't have to do appreciation strategies. We can also use RL methods, and this goes to the same kind of dichotomy when you have value-based versus policy-based methods. So usually when you have any sort of celebration you need to do, value-based methods tend to do better because when you estimate the value, you require these long traces to run over. Whereas with policies that change very quickly, it can do better when you have these fast-acting environments, right, where you need to act quite quickly. So as far as actually learning this controller for multiple agents, we can move towards using a meta controller, right? So in the case of using a meta controller, what you'd have to do is, as previously for a single agent, you'd have a single state representation and a single LSTM hidden unit, right? To learn the policy. Now you have one for each agent, right? So the simple thing to do is just combine all of them. So I have n agents, so I just combine all the states and the hidden representations for those agents, and then learn a policy, right? And now we can kind of use some information from MARLO. So MARLO, as it's currently implemented, is turn-based. So each agent takes turns to act. And so what you can do is you can just swap the Z and H as and when the agent gets to act. And also you can, the actions which aren't used, you can just mask them, right? So this is a simple way to just move towards doing multi-agent world models, right? And the alternative is to use just a single mixed density network where all of the agents use the same hidden state, right? And it's kind of useful to do this because it obviously reduces the parameters quite a bit. But also, at the end of the day, what we kind of want with multi-agents is there has to be some information that's being shared, right? And that's actually goes to the next point. So if you wanted disjoint architecture, so in the previous case, we combined all of the agents' action. What you can do is, essentially, again, what we're trying to do is maximize the mutual information between the agent's hidden states, right? So the agent should, at least in your team, the agent should have some common understanding of what's happening in the world, right? And this is this is kind of what we want to get at. And so some recent work, so this actually I believe in MALMO. This was work by Ted, one of the people we're working with. So this is essentially to use graph neural networks. And here what happens is essentially you learn a graph that kind of represents your environment in some sense, right? So it represents the interactions between agents and entities, right? And so the architecture is given there. So essentially what you do is, if you're given a state action pair, right, to 2 different time steps, the graph tries to have some information that matches what's changed in the environment, right? So if an agent has taken an action and somehow if it's placed a bomb, for example, in your graph you should be able to see that information. So and that's essentially what it's trying to do, right? And some recent results on this this architecture in MALMO has shown that this works quite well. So finally, I think one take I guess from this presentation, the takeaway is that we should probably do more model-based deep reinforcement learning. One reason is, as I mentioned, Minecraft can be quite slow to simulate runs on. So what you can do is you can learn a model, and then from the model you can run experiments quite quickly, right? And it also allows for you being able to to understand what your architecture is doing, the agent is doing, because you have a better state representation. And you also learned, a model that talks about how your environment works in some sense. Also, opponent modeling is something that people have, worked on as a kind of separate problem. But what you can do is, your opponents are essentially part of your environment since you have no control over them, right? So if opponents are modeled as part of your environment, then it's as simple as just learning a model where your opponents are whoever you're going to play against, right? So that's another thing you can do. There's also been a lot of work in using other tasks. So we talked about not having a reward function, right? So what you can do is you can add other reward functions, like for example, reward functions that in the variation auto encoder case, you're trying to maximize the reconstruction. You're trying to minimize the reconstruction error, right? So and it can be viewed as an auxiliary task, right? So it's a task of maximizing the reward while also trying to best represent your state information, right? So that's an auxiliary task. And as I mentioned, it helps with catastrophic forgetting, because when you separate the policy and the representation, now you can do multitask learning much better, because your representation is fixed, so as your policy can learn over multiple tasks. And with the model, you can also do planning. So this is similar to Dyna, right, which allows you to do a lot of planning steps before you act, and so you can get a much better policy. Right? And then finally, as we spoke about, in the case of the meta controller, it's quite easy to share the parameters, as we did here. For example, where it becomes a lot easier to reduce the complexity of the problem when you have a model, because all the agents can share the model while using separate controllers, right? So that's
So you pulled together a lot of concepts from the literature and made good arguments for why they're applicable to the MARLO task. How far are you in integrating with the MARLO framework and trying some of these ideas out?
So as far as, I guess we've completed basically we've got up to this, we finished this. So in I think the previous round was October 27th or something, right? So by then we finished the single agent one.
Okay.
And we're kind of working on the multi-agent setting now. But,
It's a good point to reiterate that the competition is still open until December 31st. So it'll be great to see how it goes.
Thank you.
Thank you.